What quantum computing is about and why it's expected to deliver fast computations. In this video, we will build together a quantum simulation that creates superposition and entanglement, those quantum mechanical properties that fuel the phenomenal computational power of quantum computers. Let's see. So, what quantum computers are about? So, quantum computers use the language of quantum mechanics. They make use of the language of quantum mechanics and perform computations. It's expected to lower the computational complexity. So, if we have here certain number of equations being solved, and here is the time for a typical problem that the computational complexity grows exponentially with the number of equations. Quantum computers expected to bring that down, and instead of having it exponential, to have it polynomial or something lower like this. So that's like sort of the quantum advantage that we get from that. To have different and several applications for these quantum computers that involve finance, logistics, portfolio optimization, machine learning, AI, encryption, and communications, and most importantly, applications in chemistry and physics. There are a lot of simulations in chemistry and physics that demand high performance computing power, but even with using and utilizing the most advanced supercomputers, still approximations are being used to perform computations to calculate properties of molecules and synthesizing of new compounds and chemicals. And for physics, to study batteries and materials, like creating new types of materials, studying carbon nanotubes, for example, and so on. So kind of simulations in chemistry and physics demand for high computational capabilities that if we have a quantum computer, it's expected to bring the computational complexity down and leverage this substantial power and make the simulations very fast. Typical quantum computing involves overlap between several fields like quantum information theory, quantum physics, knowledge about linear algebra and advanced calculus, advanced math, and also computer science. So the level of complexity in quantum computing comparing to classical, it is not on the level that you just open a notebook and start programming. You need also to understand what you are doing with it. And this we are gonna learn in this video. We are going to do create a quantum simulation that's very simple, and you can extrapolate the knowledge from this quantum simulation to larger algorithms and larger work. So accessing quantum computers is done now typically via the cloud. So if you are having your own laptop, your desktop, and then you just connect it via the internet to the cloud, then sort of the cloud would access the quantum computer via certain devices. Then you can send the information and retrieve the information. And a typical quantum computer makes use of the three fundamental phenomena: superposition, entanglement, and of course things like wave-particle duality. We are going to explore these concepts in this video, so no worries about it. We have quantum chip, that's my black box. It has an input, this is the specs of your algorithm, and it has an output, and this is typically the readout of the measurements. So in a nutshell, quantum computers, it involves quantum gates, quantum circuits, and measurements. Each one of these we are gonna explore, but we need the qubit. Just this is the quantum version of the bits to load data and encode data on them. Quantum gates to manipulate the qubits, the circuits that create certain configuration of those gates acting on the qubits in order to perform a specific computational task. And of course, measurements. And measurements here is to retrieve and measure the qubits in order to retrieve the useful information that we need. Are the qubits. So the qubits are the quantum version of classical bits. If you have here classical bits, quantum bits or qubits, we find that a bit can just be on or off, so it can either be 0 or 1. So if you find it or measure it, you will all the time find it either in 0 or 1 unless you altered its state, so you changed it. So if you have a sequence of data that is stored on 8-bit register, like this for example, then with the time you will find those numbers are unaltered, and this is the state of the bit forever unless something happens. Qubit, on the contrary, can be in two states simultaneously. It can be in state 0 or 1. I'm gonna explain this notation now. This is what the qubit could be. In that sense, we add little coefficients here and the plus. Where does this come from? So the idea of the superposition, that in quantum systems, if we have a box and inside that box we have a cat, and we put, we don't know, we came at a specific hour in the day. We have two scenarios here to continue with. Let's open the box. So we can find the cat sleeping or wake. Every time I come at 3 p.m., I open the box that the cat is sleeping inside. Either I find it wake or asleep. Then I would assume that inside the box, the cat was in combination or in two situations at the same time. It is in sleep or wake. So that's the idea of superposition. You have two configurations that are superimposing one another, and both of them are probable. However, once you open that box and look at the cat, either you find it awake or asleep, then one of these configuration is destroyed, and then you end up with one situation. It's like if we have sun, and we have the solar systems, of course we have here Earth, and then we have sort of a flying saucer. That flying saucer can come to Earth, or it can go to Saturn, for example. So if it goes to Saturn, we want to know about this intelligent alien civilization, but if it comes to Earth in a sky and in clear sky, we will see it immediately. So it's like this UFO or this flying saucer, it's in a superposition as well. Yeah, UFOs, right, it's very happy. So this is the idea of superposition, and if you extrapolate this concept to qubits, can have a qubit when we measure it. So let's imagine this is our qubit. After the measurement, it could be in state 0 or it could be in state 1. If every time we measure the qubit and find it in state 0 or 1, it means that this qubit in a superposition. This is why we write it in a superposition of two things, coefficient alpha, ket 0 plus beta, ket 1. So these are the two outcomes, and they can combine together with certain probabilities. These probabilities are reflected by those two coefficients. So in other words, to measure the qubit q and find it state 0 is actually proportional to alpha squared, to the square of the absolute value of alpha, because it could be an imaginary number, or the probability to find q in state 1 is a square of the absolute value of beta. Since we have a physical system, we must have a particle inside. It is a very closed system. It means that the total probability should equal to 1, and this is called the normalization or the norm. And then that means that alpha squared plus the square of the absolute value of beta squared, that should equal to 1. We borrowed this notation from what we call it as Dirac notation, and Dirac notation, where Paul Dirac just used those kind of notation as or borrowed them from linear algebra to describe the states in terms of vectors. Let's see how. So if we have a 2D vector that has two projections, A and B, on X and Y. Basically, we express that as AX plus BY. So that represents A as a projection in the direction of X and B in the direction of Y. If we write this using Dirac notation, we'll write that A as a vector will equal to A ket X, this is call it ket, plus the things that we write here is called ket, and if we reverse it, we call it bra. These kind of notations can make our life easier because we can express those things as vectors. And if we do that, it gives us the ability to do computations, because the main aim is to be able to perform computations and encode this kind of vectors on a computer and let the computer does the calculations for us. Similarly, if I have a 3D vector, I have the same, that vector P, where that vector P, or let's make it small b. This is the origin, this is x, y, z. This vector also has three components now, so we can write it like a plus y plus d plus c ket z. So that's the way of writing it, and if we wanted to write it in a column vector, that means that we write it in an array like this, where we put those numbers beneath one another in this order, and that represents the vector b. So Dirac notation says you can express with functions or a state of qubit, for example q, as vector. So if q takes two values and it's in a superposition of both, we can express it in a similar way. We can make the x-axis like the 0 and the y-axis like the 1, and then we can have qubit state here, and those projections will be the alpha and beta. Okay, that's fascinating. Nothing fancy about that. We only need to understand that we can express qubits in this kind of superposition. So a qubit, one qubit could be in a superposition of n typically between two values, because if we measure it, either we can find it in 0 or 1, and if we perform the measurements many times, we will get sort of correlation between the ratio of finding it in 0 or 1 proportional to the square root of those things. Now we come into the second item on our table, which is quantum gates. Typically, the gates are sort of operations or operators that perform specific action on the qubits. A typical scenario would be if you want to perform certain computation, that would mean that you can make sort of arrangement of gates specific way, and that sequence will execute this kind of execution of computation. In a nutshell, we can have sort of a library that has many gates, and we retrieve from those, we take what we need to perform computations with them. Now, before we move on, we need to understand something about what we call it the computational basis, or the size of space that I can do computation with from the qubit. So now if I have one qubit, that qubit could be in a superposition. So I have a superposition between 0 and 1. That's one case. So what will happen if I have two qubits, Q0 and Q1? Let's consider this. If I have qubit Q0 and Q1, I can have several cases where each one could be 0 or 1. So I can have a case, let's write them here, where both of them are zeros. So I can have a case where both of them are zeros. I can have a case where the first one is still 0 and the second one is 1. Can I have a case where the first one is 1 and the second one is 0. And can have a case where both of them are in 1. You see, if I count, I get here 4 states or 4 situations. So this is my Hilbert space, or the space can do computation. And if I do it for 3 qubits or so on, I will discover that this is obeys the rule of 2 to power n. So the size of that one is proportional to this 2 to power n, where n is the number of qubits. So in a nutshell, if I have Q0 and Q1, can have several configurations, and that depends on the number of qubits. And this goes as 2 to power n. In this situation, if I do a measurement, I will find the first one in 0 and the Q1 is in 0. In this one, I will find the Q0 is 1 and the Q1 is 0. In this configuration, I will find Q0 is 0 and the Q1 is 1. And in this situation or configuration, I will find Q0 is 1, Q1 is 1. So these two numbers is expressing or telling me what I will find when I measure the quantum register or both qubits. All of them are probable, then they will be in a superposition, these things. So plus, plus, plus. So for simplicity, I will choose something simple. So I have a kit of Q0, Q1. That will be alpha 1, kit 0, 0, plus alpha 2, 0, 1, plus alpha 3, kit 1, 0, plus alpha 4, kit 1, 1. So you can see how the computational advantage grows with the number of qubits, that there is more room to encode more information in the system. Because of that, if I have 10 qubits, I have 2 to power n of possibilities, and I can store many or encode many data in this superposition. So that's what gives the quantum computing its phenomenal power. Plus, the thing is that I can play with it, like playing with superposition, entanglement, and other properties. It all explore and exploits significant computational advantages beyond what's available classically. So now let's come to the quantum circuit. And the quantum circuit allows me to perform a certain computation. It includes qubits and sequence of gates, and of course measurement gates. And for the measurement, we need to store the outcome. So if I measure in those bases, 0 or 1, I can have here as a result either 0 or 1. Similarly here, 0 or 1. So that number, I need to store it somehow. This is what we put it on what's classical bits. So since I do here 2 measurements, I will create 2 classical bits, and basically we load that number and store it here. It doesn't have a memory. So once I do the measurement, I need to store that number. So it could be here, for example, 0 or 1 and so on. So in a nutshell, that's called register, and this is called classical. Those are my gates, and to work in quantum computing, I do move forward from left to right, and I perform the computations. Here we have to mention one very important fact. If I have a quantum circuit with certain gates, so on, and I move forward, I should also, or I have the ability to move backward as well. So I can retrieve the original states of the qubits. Unless this is bending that, I didn't perform no measurements. I didn't perform any measurements. Before the measurements, I can move forward and backward. If I do the measurements, the whole system will collapse in superposition, and I have only classical outputs or classical values. So I can't do anything about them. So the idea of moving forward and the backward is pure quantum mechanical. That's called unitarity, coming from the unitarity. And the unitarity means that those quantum gates should be unitary because they act on qubits, and those qubits are physical systems. So if you go forward and you make the inverse, that should be identical because qubits are something that's physical, obeys the laws of quantum mechanics. That's in complete contrary to classical gates, where in classical gates, if I have gates like and I have two inputs, for example 0 0 0 1 1 0 1 1, I will get here 0, I will get here 0 0, and then here I will get 1. Can't reverse this one because I have only one output. So that output doesn't tell me which configuration. If I have 0, I don't know which configuration I was in. Is this 1? Is this 1? Is this 1? I don't know, so I cannot reverse this operation. So hence, quantum mechanically, I can reverse the gates, but classically, I can't. But then how to perform computations using quantum computer? And the answer is simple, is that we need to construct quantum circuits that has a sequence of specific gates and way of doing the measurements, perform the computation. So that's how we want to do it, and then those gates have specific actions on the qubits to alter its state. So I can get a question here, why we can't use classical gates and borrow them for a quantum computer? This is basically it. We are acting on quantum mechanical systems, and that would require specific action from quantum gates that can manipulate those physical systems. So in that sense, we cannot borrow classically gates to act on them. Second thing, those actions or those quantum gates should be unitary. They should be reversible. And this is not the case in classical gates or the more than one bit classical gates. Now we wanted to understand quickly what is the action of each gate. So we will go to our library, and then we have in our library certain gates on the shelf. We will just borrow now H and X and CX gates. The H called Hadamard gate, Pauli X or Note, and CX is called controlled Pauli X or controlled C Note gate. Using those three, we can create an entangled circuit, and we will see now in a minute. Let's now figure out the action of those gates. We'll come into the action of the first gate, which is the Hadamard gate or H gate. And that one, if I am given a qubit, single qubit, so I would imagine quantum computer of a single qubit, then this Q will be initialized or will be in a default situation, will be in a kit 0. So that's ground state. So I have here a qubit initialized. This is the initial, and the initial is kit 0. Now we'll come into the action and we'll apply the gate. What Hadamard gate will do, it will put the qubit in a superposition. So instead of being in 0, pure 0 kit state, it will put it in 0 and 1. So it will push it to be in a combination between the 0 and 1. And if you notice, this number is related to the normalization. So if you square it, you will get half, and this is multiplied here and there. And then it means that half of the time we will find the qubit in state 0, and the other half will find it in 1 if we run this experiment for 100 or 1000 times. So that gives us an idea about probabilities that are involved. Of course, that's important for normalization. It means that if I add the square of that plus the square of that, get half plus half, I get 1. So H acts on qubit in a ground state in a superposition. So that's the action of the Hadamard gate. So now let's come to the X or the C node gate. And this is basically for our one qubit quantum computer. If I have here qubit that's initialized in 0, then X will just flip it and make it 1. So this is the action of X gate on the qubit. Let's now see what will happen if we combine both together. I have here two qubits. They are initialized to kit 0 indeed, and let's write the state of this. So both of them are zeros, and this is definitive state. So the starting state is 0 0. Now let's apply Hadamard gate. So this is my first action. So if I apply the Hadamard gate, what this will do, it will put this qubit Q0 in a superposition. So I will get here 0 and 1. So in a nutshell, after applying Hadamard gate, the first one I will get 0 plus 1 0. because the first one has been translated into a combination between the kit 0 and the kit 1. Second qubit is still unaltered because nothing happened to it, still in state 0. We only acted with H on the first qubit, so in that sense we have put it in a superposition. Now let's apply a second action, X gate, and that's what will do. It will flip the second qubit, so I will get the same but 1 for the second qubit. That seems logical. Let's now introduce another gate, C node, and this is what we need to create the entanglement. So the C node gate, if I have 1 qubit, it will not work because it requires, or it's called qubit gate, and that gate has sort of a node here. This is called the control, and this is my gate X. And if I have 2 qubit quantum computer, the control sort of will be attached to one qubit or a single qubit, and the gate will be acting on the second one. So the gate will act on the target qubit, and this node will be at the control qubit. And the idea of that control is to sample what happens to the first qubit. Is it 0 or 1? So someone will ask me, okay, how we would know the state of the first qubit? And the answer is not. We can't. We have to work with the scenarios. So we have two scenarios here. If, for example, I apply Hadamard gate, then I will have either 0 or 1 based on that value. If it is 0, the first one, second one don't do anything. If it is 1 with the given gate, which in our case is X. So if I make it here, so the node will sample what happened. So if Q0 is in state 0, do anything, Q0 is 1 with X gate. And this gate is very important for the entanglement, for example. So now let's see, cover now the meaning of the entanglement. So imagine we have 2 qubit quantum computer. I have a first qubit, the second qubit, this is qubit 0, this is qubit 1. Both are initialized to 0. Then I will make my first action, which is applying Hadamard gate. That action would result to me into putting Q0 into superposition. So I will get here, kit 0 plus kit 1. So in that sense, this is my starting, act with H, I get here position, and then I make my second action. Now I put the C node gate, and that control will sort of look by imaginary measurements by the eye. What is Q0? It is in a superposition. So I have to work with the two scenarios, like the flying saucer that goes to 2 planets. I can assume a scenario where the qubit is 0. So I will tell that qubit is 0, don't do anything. So both of them are zeros. So if the first one is 0, don't do anything. But if the first qubit is 1, then apply X gate. And what X does this into 1, qubit 1. So it will flip and make it 1. And here we come to a very important conclusion in quantum computing. This is, we call it highly mixed state or in highly entangled state. So if I make a summary of that, I have here Q0, Q1. First act with H, that H put it in a superposition, and then I act with a C node gate that has a node here. And that node sort of a control that tells me what action I should do based on the value or the state of Q0. The first action, if it is 0, don't do anything here. So leave it 0 as it. If it is 1, flip, activate this one, make it active, and then flip Q1 to 1. The first action give me this particular state because the first qubit, now it's in a superposition. The second is still altered. The second action, I look to the first qubit. The first qubit here is 0, so don't do anything to the second. I leave them 0, 0. If I go to the second state is 1, so the control will tell, okay, if I have a first qubit is 1, the second should be flipped using the X gate. So then that will be 1, 1. And here, this is an entangled state. Why? Because whenever I measure or I do partial measurement, let's say we will do, for example, one measurement for this qubit, the second qubit, state of the second qubit will be known immediately, because if I find the first qubit to be in state 0, so measure, find Q0 to be in 0, then immediately I don't have any option. I have only a situation or configuration where the second qubit will be 0 as well. And similarly, if I find the Q0 1, then Q1 will be in 1. And this is why it's called entangled state, because you get information about the other qubits for free. It's like a correlated measurements, highly correlated measurements. And now there is big difference between that, because entanglement means that if you know a person, you have a twins, and you talk with the first one, then you know the second one immediately. However, superposition is just only you make or you maximize or you build the probability of situations that you have. So instead of being sitting the whole day in the flat, you might be walking in the street, because some of your friends asked you to walk in the street. So you have two situations. In that sense, if I have Q in state 0, I put it in a superposition, then it will be in state 0 and state 1. Entanglement means that it happens for more than one qubit. Q0, Q1 would mean put the normalization first. If I measure this one, the second one will be fixed immediately. So if Q0 is 0, Q1 will be 0, and if Q0 is 1, Q1 will be 1. By that, I hope we have created a minimal quantum algorithm and a quantum simulation that shows and represent entanglement and superposition.